Hello, everyone. Today we're looking at work done by non-conservative forces. Just a reminder that work is the transformation of energy between different forms or the transfer of energy from one object to another. We know work is force times displacement, but work is only done when the force is parallel to the displacement. So if that force is causing the object to move or causing it to speed up or slow down, that force is doing work, and that is a measure of the change in energy on that object. Now, what we have done so far is assuming that the force is constant, just like our kinematic equations only work for constant accelerations. But what would happen if we had a force that was changing? And we do have some tools at our disposal. If we were to graph the force versus the displacement of the object, of course, if the force is constant, then we just do force times displacement. But if we think about that graph, what is it that we're really calculating? Well, force times displacement, the y value times the x value, we're really doing the area under that graph, or the area bound by the force versus displacement graph. So if the force were variable, if it were changing, right, how would we handle this? Our equation sheet tells us to do force times displacement, but that's assuming a constant force. If the force is changing, then we would handle it with our tools for handling graphs, and that is, we're just going to find the area bound by the force versus displacement graph. So keep that in mind. If we see a force versus displacement graph, then the force is changing, then we're able to do the area underneath in order to calculate the work done. And any area below the displacement line would be negative work being done. We know negative work is when energy is leaving the system, something like kinetic friction or drag that will take mechanical energy away from our object. And positive work, when the force is in the same direction as the displacement, we know that's energy that's added to the system. So maybe that's a propulsion system, or maybe that's somebody giving an object a push to make it speed up. Okay? Conservative forces are any force that's related to a potential energy. So we're looking at force of gravity, spring force. They're related to gravitational and elastic potential energy. And specifically, conservative forces are going to keep the total mechanical energy constant. So they have no effect on the total mechanical energy of the system. They are just taking from the kinetic energy pile and giving to the gravitational potential energy, or vice versa. So conservative forces are transforming energy from one type to another within our system. So energy is not coming in, energy is not going out. It's just changing from one type to another. Okay. They are also path independent. So we'll take a look at what that means to be path independent. So imagine these three different pathways for this block to get to the bottom. So I have here just a frictionless incline. If I were to do maybe a little bit more exciting, a frictionless loop-to-loop, or this one over here, which is just in free fall. And I want to imagine the free body diagram on each of these objects. So going down the frictionless ramp, we have Fg and Fn. For the frictionless loop-to-loop, so I'm going to say mu equals 0 to make it frictionless. The free body diagram is going to continue to change, right? We have normal in gravity and normal in gravity, and really it's very dynamic. But one thing you're going to notice, everywhere on that ramp, the normal force is perpendicular to the motion of the object. And if the normal force is perpendicular to the direction the object is moving, just like it is for our incline, as that cart slides down the ramp, the normal force is perpendicular to the velocity, which means the normal force is not doing any work. And if the normal force is not doing any work, then it's just the force of gravity that's doing work. And the force of gravity is a conservative force. So we know that the total mechanical energy of our object is not changing. The same thing for an object in free fall. The force of gravity is the only force on the free body diagram, so the total mechanical energy of that object shouldn't be changing either. And what that means is, for each of these objects to reach the bottom, we know that their total mechanical energy is staying the same. So while they all start out with the same GPE, because they're the same height above what I'm using as my reference level down here, which is the ground reference level, they're all starting with the exact same gravitational potential energy. At the bottom of the hill, they should have kinetic energy, but since only a conservative force is causing the objects to speed up, then we know the total mechanical energy is conserved, which means the kinetic energy at the bottom is equal to the gravitational potential energy at the top. So for each of our three pathways to get to the bottom, even though the one in free fall gets there a lot sooner, they're all traveling at the exact same speed when they get to the bottom. Okay? Because our gravitational potential energy is turning into kinetic energy, and then we could solve kinetic energy to get our speed. Kinetic energy is 1/2 mv squared. So our speed is just 2 times the kinetic energy divided by the mass, and then we would take the square root. Okay? When we look at non-conservative forces are going to be things like kinetic friction or drag that are going to take mechanical energy and they're going to turn it into a non-useful form, a form of thermal energy that we can't recover and turn back into mechanical energy. So basically that means that energy could be leaving our system if it's negative work being done by non-conservative forces, or if it's something like a propulsion system or somebody giving it a push, we could have energy coming into the system. So new energy that our system didn't have yet. So incoming energy would be considered positive work and outgoing energy would be considered negative work. So we see our total mechanical energy is decreasing for things like friction, drag, and other non-conservative forces that are doing negative work. Okay? Non-conservative forces are path dependent, which means the longer you experience a non-conservative force, the more energy is going to change, the more your total mechanical energy is going to change. So we know work is force times displacement. So if you experience a non-conservative force for a longer displacement, then it's going to do more work, and that's going to be a bigger change in energy. So I have here two ramps of the same material. They both have friction, and what I'd like to know is which path would the block be moving fastest at the bottom. So I take the same block with the same mass and the exact same GPE to start with, the exact same gravitational potential energy to start with. But when they get to the bottom and they end up with just kinetic energy, so I'll write kinetic energy at the bottom, the question is, what has happened to my total mechanical energy? Well, I know if we have a dissipative force like friction, I know that we're going to be losing some energy to thermal. So our mechanical energy is decreasing, which means the leftover energy at the end is less than what I started with. But for the ramp with the loop, I'm experiencing that friction for a much greater distance. And if I'm experiencing friction for a greater distance, that means friction is going to be doing more work. So there's going to be more energy that gets wasted in the second case. So in both cases, the amount of kinetic energy left over is less than what I started with because I also have this amount of thermal energy. But in the case of the loop-to-loop, I have even less kinetic energy at the end. So I'm going to make that KE really tiny. That looks like as small as I can make it. But there is more thermal here because friction was able to do work for a longer distance and it was able to dissipate more energy. So the one that's traveling fastest is the one with the highest leftover kinetic energy, which is going to be the shortest pathway. And in this case, the straight line is the shortest pathway. Okay, so that's all I want to talk about here for work done by non-conservative forces. Thank you for watching.